Alright, so in this video we're going to do a lot of practice problems that might be on the exam, might not be. And I hope this helps you, right? So we're just going to jump right into it. I want you to write out a Lewis structure for this molecule, and I want you to assign the formal charges on the correct atom. If you want to pause the video and do it on your own, you can, but if you want to see me do it, I'll do it. Right, so we first have a CH3, and whenever you see a CH3, you just kind of want to do it right off the bat. Just instinctively know that carbon is going to be connected to 3 hydrogens, and that carbon is going to be connected to this oxygen right there. Let's do that. And of course, this oxygen has 2 hydrogens connected to it. But we need to assign the formal charge too. Let's count out the bonds, because carbon is already satisfied. It has 4 bonds, but oxygen has 3 bonds, so it's going to have some lone pairs. And whenever you see a bond, just say 2. So 2, 4, 6 electrons, right? And oxygen wants 8. So 8 minus 6 is 2 lone pairs, right? Okay. If you know chemistry, then you would know that oxygen has 6 electrons already in its grasp, right? So we have 6 electrons, and we have 2 electrons right there, so that's 1 and 2. So we have 2 electrons outside. We're going to subtract it. It will give us 4 electrons. All right. Now we're going to count the bonds that we have. That is 1 bond, 2 bonds, and 3 bonds. So 4 minus 3 is a positive 1 charge, right? So oxygen therefore would have a positive 1 charge for the oxygen. Again, we count the electrons that the atom would already have. For this case, oxygen has 6 electrons, carbon would have 4 electrons, just right out the bat. And we would then subtract the electrons that it would have against the lone pairs, each individual electron, right? So 6 minus 2 is 4, and then subtract the bonds in total. So that's 3 bonds. So 6 minus 2 is 4, and 4 minus 3 is positive 1. And so that's how you would do that problem whenever you're asked to make a molecule and assign formal charge. Right, so it's the same problem. I just want you to write out the molecule and then assign formal charges. So pause the video and do it on your own. Alright, well, I see that we have a CH3. It's on the very front, so it's going to be C with 3 H's, right? And we're connected to a carbon. Alright. Do I want to connect the carbon like this with an oxygen? Well, I wouldn't want to do that, because then, carbon right here would have 3 bonds to the 2 hydrogens, so that's not going to work for me, right? What I want to do is make an oxygen right there, and notice that carbon has 3 bonds, but then again, oxygen just adores having 2 bonds. So that's an oxygen with 2 bonds. You could count the formal charge, so that would be 2, 4, 6, 8. 6 minus 4 is 2, and 2 minus 2 bonds is neutral, 0, so it loves it. So that's great. Carbon has 4 bonds, that's amazing. So we're going to connect oxygen to the carbon and connect this carbon to 2 hydrogens and connect this to an oxygen. Again, oxygen has 2 bonds. It's great, neutral. Carbon has 4 bonds, hydrogen has 1 bond. But what about this oxygen? Do I connect it to the sodium? No, I don't do that, because sodium is a metal, and metal is an ionic bond. Ionic bonds actually occur, for instance, like this. We're not really bonding. to the other atom. It's more like a electric magnetic bond. So they're not physically touching, they're not physically connecting, they're kind of just vibing far away. So we will have our sodium or any type of metal just away from us. Since that is partial positive and our molecule in total has to be neutral, that means that our molecule right here has to be negative, because a negative and a positive give you a neutral, right? So to cancel out this positive molecule, I need this molecule to be negative. So what's going to be negative? Well, let's see. We have 2 right there. So 2, 4, 6, and 8. Just count out the electrons like I did. 2, 4, 6, and 8. So in total there's 6 electrons around us. So oxygen has 6 electrons to begin with, and we have 6 electrons around us. So in total that gives us 0 electrons, and we want to subtract this bond. So 0 electrons minus 1 bond is a negative charge. So in total that would be a negative right there. So the oxygen is negative, and it doesn't matter if your molecule is neutral. This molecule right here would be negative, because the negative and the positive cancel out, right? So again, make sure that carbon has 4 bonds, oxygen usually has 2. If you want to count the formal charge for oxygen, just go 2, because there's 2 electrons making this bond, and then just count up to 8. 2, 4, 6, and 8, right? And then we're going to subtract the valence electrons that we expect our atom to usually have. So oxygen usually has 6 electrons, so 6 minus the 6 lone electrons that we have, that's 0. 0 minus the 1 bond is -1, and that gives us a negative charge. It's the previous problem, like before. Just do it on your own, or you can watch me. We have a CH3 right there, so instinctively I know it's also in the end. It's usually terminal. We know that it's going to be like this with your hydrogens on the end. That's a very bad H right there. Connect this to a carbon. I usually have my hydrogens branching out. It's never like this. Just no, don't do that. And I don't want to do this. It just looks weird. Carbon has 2 bonds, not good. Don't do that either. So we're just going to directly link carbon to another carbon and do the same thing. So that's an H, right? That's an H right there. And connect this to a carbon with an oxygen, a nitrogen. That nitrogen has an oxygen as well. Usually that's just like the skeleton, but then we're going to have to go back through a molecule and make sure that our bonds are proper, right? So this carbon has 4 bonds. That's cool. And this next one only has 3 bonds. We always want 4 bonds, right? So I can't make a bond to hydrogen because hydrogen only has 1 bond. And I can't make it like that because carbon would have 5 bonds, and that's not good. So the only logical thing I can do is make another bond with a carbon. Okay, so now this carbon has 4 bonds, so it's good. And what about this carbon? This carbon has 3 bonds, right? And it's attached to an oxygen, and as we know, oxygen likes to have 2 bonds, because then it would be neutral. So the best thing that I can do for this molecule is connect it to 2 bonds right there. Okay, so if you want some practice, this would be a alkene right there, right? And this would be a carbonyl, which is not a functional group. It's more of just a standard name that you would give. And this would be your classic amide right there. Okay, so we need to figure out the formal charge for this molecule. Usually it's the thing at the end, but if you know that oxygen is neutral, carbon is neutral, then it's usually the nitrogen that it's attached to. So how many lone pairs does this nitrogen have? Well, we have 2, 4, and 6 electrons, and we always want 8 electrons, so it's 7 and 8 right there. Okay. Nitrogen usually has 5 electrons. So 5 minus 2 electrons gives us 3 electrons. And we have 3 bonds. Those 3 electrons minus 3 bonds would give us 0. So this whole portion would be neutral. And so this whole molecule would be neutral in itself. For this problem, I want you to write out the resonance structure for each molecule and then determine which molecule would be the more proper hybrid. So which one would contribute more to the resonance structure? Which one would we prefer? Okay, so here's a quick tip to do. Notice that this negative is attached to this carbon, right? Well, the thing with negatives is that they can travel, They can kind of travel for every 2 molecules, right? So what we're going to do is we're going to move it. That's 1 molecule, or I should say, it's going to go here, right, to this carbon, and then from that carbon it's going to go to this this oxygen. And likewise, this double bond is going to move only one atom, right? It's only going to move to one neighbor. So this double bond is going to split into this carbon. Okay, so let's write out the new structure. The new structure is going to have your normal carbon base and again a double bond, because that double bond came from the oxygen, and double bonds can only move to one molecule or to one atom. Negative charges can move up to 2 atoms, always 2 atoms. It never, if you have a negative that only moves to 1 atom, that's incorrect. It always moves 2 atoms, okay? So we're just gonna have this right here. It's a single bond now. And we have an oxygen. And that oxygen will now have the negative sign. We'll have the negative sign. Because if you were to count this out, you have 2 electrons, 4, 6, and 8. 6 minus 6 electrons is 0. 0 minus 1 bond is -1. And so that negative that was on the carbon just kind of drove on the highway and moved only 2 atoms. It moved from 1 carbon, 2 carbons, or excuse me, sorry. It moved 1 carbon and then 2. Okay? Awesome. So which one would contribute more to the resonance structure? Well, when you're looking at this, you want to have the more bonds. That's the first thing you look for, is just bonds. If one molecule has 3 bonds and the other molecule has 4 bonds and everything is correctly placed, then you want the one with the most bonds. Because if you had a bundle of sticks, right? If you had 5 sticks, it would be hard to break it. But if you had 2 sticks, it would be pretty easy to break it, right? Yeah. So let's count. We have 1, 2, 3, and 4 bonds right there. Okay. Well, we have 1, 2, 3, and 4 bonds right here too. So the bonds are equal. What do we do when the bonds are equal? Well, when the bonds are equal, we instinctively go to the negative charges, or electronegativity. So is a neutral oxygen better than a negative oxygen? Well, no, because we always want to go to the most electronegative, right? So I'd rather have a negative oxygen than a positive oxygen, okay? So always check for your bond numbers. If they have equal bonds, then you go to electronegativity. If the oxygen is more electronegative than the other molecule, then it's what we would prefer. And so for this case, since oxygen is negative, which it tends to typically be, then you pick that one. it contributes more to the resonance. Okay. Let's do the second one. All right. The second one. Well, oxygen is positive and it usually doesn't like being positive, so I kind of want to make it negative. How am I going to do that? How am I going to do that? Well, let's see here. I can just, yeah, I can. All right. Well, I can actually transfer an electron right here, right? Because let's count out these electrons. That's 2, 4, 6, and 8 right there. Let's do it in a different color so you can see it. That's 8 electrons, all right? So 6 minus 2 is 4, and 4 minus 3 bonds is positive. Well, that's not good. How can I fix it? Well, I can actually transfer an electron right here, and so I would have this oxygen bonded to a hydrogen. Hydrogen is fine. And then a carbon, well, a carbon right there. And what would be the formal charge? Well, let's see. It would be 2, 4, 6, and 8, right? So 6 minus 4 is 2, and 2 minus 2 bonds is neutral. So 6 minus 4 is 2, 2 minus 2 is neutral, and so this would have a neutral charge, right? And let's see, 2, 4, 6, 8, 4 minus 2 is 2, and 3. Yeah. Well, which one would contribute the most to the resonance structure? Let's count our bonds. 1, 2, 3, 4, 5. 1, 2, 3, 4. Yeah, it doesn't matter that oxygen is more negative compared to this oxygen, because the first thing, literally the first thing you check for is your bonds. We have 5 bonds right here. We have 5 bonds. And this one only has 4 bonds. And so which one is easier to break? The one with the 4 bonds. It doesn't have that much stability. And since we have 5 bonds right here, it's more stable and it contributes more to the resonance structure. So again, the first thing you want to look for is bond, the number of bonds, and then after that, you go to electro negativity. Right? For this problem, I want you to write the line or the skeleton molecule for this molecule. So I want you to do like the line structure for this one. It's pretty confusing if you're not used to it, but this right here, this whole shebang, is that we have 2 of the same molecules connected to this carbon, and that carbon is connected to that oxygen. All right. So we have, usually for this kind of problem, you just want to draw out the Lewis structure and then write the line structure for it. So we have a carbon, and that is connected to an oxygen. And then we're going to have 2 things connected outwards. So we have a carbon that has an H right there. Or sorry, that carbon is going to have some H2. It's connected to another carbon that has 3 hydrogens. Right? So CH3 right here, CH2, that is connected to a carbon, and it's going to be the same thing on the other side. So CH2, that carbon is connected to a CH3. All right. Well, that's 1, 2, and 3 bonds. Carbon always wants 4 bonds, so I instinctively know that this carbon is going to have what? A double bond to the oxygen. And oxygen is happy too. It'd rather have 2 bonds than 1. now that we've drawn our line formula, we're actually going to have well, not our lines. Now that we did our Lewis structure, we're going to have our lines. So let's do that. And I'm going to show you how to do hashes and wedges, even though it's not required for this problem. I want you to be comfortable. All right. Okay. So for every carbon, that's going to be a point, and we're just going to go up, down. That's 3 carbons, then up and down. All right, so 1, 2, 3, 4, and 5. That's 1, 2, 3, 4, and 5. All right, so 1 and 2, and this is an oxygen, so it's going to be, since we're pointing downwards, I'm going to have my oxygen right here. I'm not going to do it like this. It looks pretty bad. Okay? And for this one, for this carbon, we have some hydrogen, so I'm just going to kind of do like a little wedge right there. Put a hydrogen. You can put another hydrogen right here. And we have a triangle, kind of like a wedge. That means it's shooting outwards towards you, so it's coming from the computer screen going towards you. And we're going to have these hashes, meaning that it goes backwards into the paper or into the computer screen. In this case, carbon has 2 hydrogens connected to it because we have 1 hydrogen just kind of hanging out. And when we're pointing upwards, when our peak is up, we will have a hash right there, or a wedge. Another hydrogen, go back, another hydrogen. Since this is going up, we have a wedge, hydrogen, and another hydrogen. Since this is going downwards, we have a wedge going downwards, some wedges, or some hashes right there, and some hydrogens. Of course, if you don't want to do the hashes and wedge, it would just look like this, and you'd be done. For this problem, I want you to tell me the hybridization, electron pair geometry, and approximate bond angles for the indicated molecules or indicated atoms. Okay, well, let's, if you want to be on the safe side, just draw out the molecule and Lewis structure, kind of just like fragment it. So H2N would become N, and we have hydrogen right there, and it's connected to this carbon. Okay, so it's a nitrogen connected to carbon. Well, you would think that it's 1, 2, and 3. Well, you would think that it's a sp2, right? But you'd be wrong, because you always have to consider the lone pair. So 2, 4, 6, that means we have an electron right there. So that's a lone pair. And nitrogen carries 5 electrons, so 5 minus 2 electrons. 5 minus 2 is what? 3. And 3 minus 3 is neutral. But you just had to know that nitrogen has invisible electrons. That was the important thing. And we have how many things surrounding nitrogen? Well, we have 1 bond surrounding nitrogen, 2 bonds, 3 bonds, and 4 things. So a lone pair counts as an electron group. An electron group is just a fancy way scientists say something that is surrounding an atom. So we have 3 electron groups, or electron zones, I would say, as bonds, and one of them is a lone pair. Lone pairs count as 1 electron zone, okay? And since nitrogen has 4 things, it's pretty simple to figure out the hybridization. S1P2, or I should say P3, sorry. So 1 plus 3 is equal to 4, and we have 4 things surrounding us. Alright, so that's just kind of like a tidbit tip, a little trick, if you will, to understand how to do hybridizations. So we can say that this is a sp3. The 1 is invisible. That's the hybridization. And what is the electron pair geometry? Well, for sp3, you just have to know it. It's tetrahedral. Tetra is 4, so be tetrahedral. And the bond angle for tetrahedral is 109 degrees, approximately, right? Okay. What about C3? What about this carbon? Well, this carbon has 1, 2, is surrounded by 2 electron zones. But then you have to notice, you would have to know that this carbon, we're not focusing on the smaller carbons, we're focusing on this one, has some hydrogens. And so 4 things also surround it, that being 1, 2, 3, and 4. Those are 4 electron zones, meaning that we are an sp3. We are an sp3 formation. So it's the same thing. That goes that. We also 109. So let's call that tetrahedral. And this carbon 5. So what's here? That carbon 5, right? Carbon 5, it looks like this. Carbon double bonded to another carbon and is bonded to another carbon. Okay? So how many bonds do we have? We have 1, 2, 3. Carbon always wants 4 bonds, so we have a hydrogen right there. But this is not sp3. This is actually sp2, because it doesn't matter if it's a single bond, a double bond, or a triple bond, or even a quadruple bond, which we'll get into later, not in this class, but it doesn't matter how many bonds are in one zone. It's just a zone. So you can have a triple bond that is still one zone, right? You can have 2 bonds that is still one zone. It's like thinking, okay, well, you have one person in a house. That's a house. That's one zone. And that's one person in a house. That's one zone. But then you have 2 people in a house. How many houses do you have? Well, it doesn't matter if you have 50 people in one house. It's still one house. If you had 50 people in 2 houses, then it would be 2 houses. But in this case, this is a house that has 2 people in it. And so that counts as one house, one electron zone. All right, since we have 4 bonds, carbon can only support 4 people in total, and those 4 people are in 3 houses, then we would have an S, 1, P, 1 plus what gives you 3, right? 1 plus 2 gives you 3. So that is a sp2. And sp2 is classified as a trigonoplanar, right? Trigonoplanar is 120. So you can think of like 1, 2, and then you don't have anything here, so it's a 0. 120, that's pretty cool, right? 1, 2, and 0, 120. It's my little tip for you. And we have the C8. All right, we have a C8 right there. Let's do this in a nice lime color. So we have a C, and we need to figure out the hybridization. Okay. We have a carbon. That carbon is connected to this other carbon and is triple bonded to another carbon. Okay. How many bonds do we have? We have 1, 2, 3, and 4. Well, there are no hydrogens, because if there were a hydrogen, you would have 5 bonds, and that is illegal. You would go to prison for that. So there's only 4 bonds, and how many electron groups, or how many houses do we have? 1 house, 2 house. So that's another house right there. That house has 3 people in it, but it's still just a house, right? So in total, we have 2 houses, or 2 electron zones, if you want that. You have S1 plus S1, because 1 plus 1 gives you 2. So that's just a SP. And really it's just like this. So it's linear, right? Linear. And it's just 180 degrees. Also, it's important to know the lengths of each bond. So this bond right here is pretty long. This double bond is a medium length, and this triple bond is a short length. So imagine a stick that's just long, right? And then you break that stick in half. So it becomes this. And then you break one of those sticks in half again, so you would have this. So the more bonds you have, the shorter they are. If they're a triple bond, they're the shortest. If they're a double bond, it's a medium length, and if it's a single bond, then it's the longest. For this problem, I want you to circle the one that has the higher boiling point. So we want a high boiling point. Okay, well, notice that compared to each one, right? So out of the pairs, you gotta circle which one has the highest boiling point. So this is gonna be pair 1 and 2 and 3, right? Which one in 1 is gonna have a higher boiling point? Well, I would say this one. Because we have a hydrogen bonding, right? Hydrogen bonding occurs because normal bonding is not H enough, right? It's not enough, H enough, whatever. But hydrogen bonding only occurs with nitrogen, oxygen, or fluorine. In this case, this one does not have a hydrogen in it, or it does have hydrogen, but it's not directly connected to an oxygen. Oxygen has 2 bonds, therefore it's pretty happy by itself. But this one, this oxygen is connected to a hydrogen. And if you want to know functional groups, that's actually an alcohol, alright? It's actually hexanol. So in this case, hydrogen bonding leads you to a higher boiling point because it takes more energy to break that H bond, alright? Cool. What about this one? Well, there are no oxygens, there are no hydrogen bonding, so what do? Normally, you want to count the one that has the most carbons. So we have 1, 2, 3, 4, 5, 6, and 7. 7 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 carbons. Since we have more carbons, there are more London dispersion forces, right? There are more dipole moments. So the bigger the molecule is, if they don't have any oxygens or H bonding or whatever, it just comes down to size. The more carbons you have together, the more London dispersion forces they have. And therefore, it would be this one, since we have more London dispersion forces. Alright. And right now, it's not really a competition. You have an oxygen compared to carbons. This actually experiences a dipole moment. So it would be polar. And since it's polar, it requires more energy to break this oxygen and carbon bond compared to just normal carbons and hydrogens, right? So it'd be this one, since we have a polar molecule. If you want to think about it in simple terms, this has oxygen, this doesn't. So this one would have the greatest boiling point. For this problem, I want you to write out the line structure for this molecule, and I want you to do the hash and wedge. All right. So I noticed that we have a CH3, which is a methyl. All right. So since we have a CH3, it follows that we would have a carbon attached to 3 hydrogens. It's at the end. So notice that this is at the end and that's at the end. Those are terminal carbons. It's attached to another carbon that has a hydrogen, and then that carbon is connected to a carbon that has a hydrogen, and it's connected to a carbon that has an oxygen, and another carbon that has 2 hydrogens. Notice that I'm just doing straight down the line. I'm not worrying about bonds because I go back to the molecule and worry about bonds later, right? I would recommend doing this in pencil. Where were we? Carbon connected to oxygen, other carbon connected to 2 hydrogens. Then we have a nitrogen that is connected to a hydrogen. And of course we have a carbon connected to 3 hydrogens. Alright, well this carbon wants to have 4 bonds, so we're going to bond it to this carbon, because this one would have 5 and that's not good. This one has 4, that's good. This one has 1, 2, 3, and 4, that's also good. 1, 2, and 3. This one has 4, so I cannot do this. This is illegal. Carbon would have 5, right? So we have an oxygen. I usually know that oxygen has, or wants, 2 bonds to be neutral. So that's good. Carbon, carbon. All right. We cannot make a double bond because carbon would have 5. Same thing for here. So let's count out the lone pairs. So it's 2, 4, 6, and 8. 5 minus 2 is 3, and 3 minus 3 bonds is neutral. Okay, cool. Let's draw out our line structure. So 1 carbon, 2 carbons, 3 carbons, double bonded, 3, and 4, double bond this to an oxygen. Our peak is going up, so our oxygen goes up, right? 2, 3, 4, or 3, 4, 5, 6, sorry, 6, and 7. Let's see, 1, 2, 3, 4, 5, 6, and 7 carbons connected this to an carbon right there. So let's double check. Always double check. Yeah, 1, 2, 3, 4, 5, 6, 7, 8 things. 1, 2, 3, 4, 5, 6, 7, 8. All right. Now we're going to do hashes and wedges. We go down. Our peak is down, so we go down. Hash. Hydrogen, hydrogen. We go up here. Well, actually, you don't need that because it'd be kind of weird, right? Because you would have a wedge and then hydrogen, and then you don't have anything in the back. We have 1, 2, 3, 4. That's not good. You only do it when you have like 2 things connected to carbon. In this case, hydrogen would just be in the air by itself, so it's not good. We're just going to leave it like that, implied. All right. The same thing for this little carbon in the bottom. And then carbon right here, we don't have anything connected because it's connected to an oxygen. Well, we do have something right here. So we're going to have a wedge and a hash. All right. And a wedge and a hash again. So let's see, carbon, carbon again. And this is a nitrogen. This is a nitrogen, so we're going to label it as a nitrogen. Nitrogen. And here's an important thing. Electrons, this electron group counts as, well, a zone. It counts as a house, and you put your houses in wedges and hashes. So it's connected to a hydrogen and another hydrogen. So there are 2 things that are in the air or on the ground. Therefore, we have a wedge and a hash. And for demonstration purposes, we're going to make this really bold. An electron goes on a wedge or a hash. It doesn't matter if the electrons are in the back or in the front. Just make sure that lone pairs count as groups that can be put in 3D. Okay? So if you had this nitrogen, that'd be incorrect because it would need its lone pairs. Right? Okay. So, and then again, this is wedge and hash. I want you to rank each molecule from 1 through 4, 4 being the lowest and 1 being the highest, right? And rank them in the solubility in water. So which one is more soluble? The main thing you want to focus on is that H bonding, right? It's that H bonding. H bonds are pretty polar, right? And water itself is polar. Here's a water molecule. This bent structure gives us a dipole moment that makes us bent and therefore makes us polar. So therefore, I need something that itself is polar. Okay, well, instinctively I know that this is not polar, it's just carbons and hydrogens that's not polar. So I know that this is going to be number 4. It's pretty terrible. This one is polar, but it doesn't have an H bond. And I know that H bonds, hydrogen bonding, is greater than just plain old polar, just oxygen, right? It's greater. So this is number 3. And now we go into the alcohols. This is an alcohol group. Same thing for this one. Which one is more polar? Well, you gotta count the carbons that it's attached to, because you could treat carbons like grease, because when you eat something fatty, it's just a fat composed of carbon and hydrogen, so you don't want anything fatty in your water, right? It's like oil. So you count your carbons, that's 1 carbon, 2 carbons, 3, 4, 5, and 6 carbons. Okay, 1, 2, 3, and 4. Well, 6 is actually pretty bad. And here's a mnemonic for you. When you hit 6, the water is sick. And water does not like to be sick. Do you want to drink sick water? No. So 6 is sick. And therefore, it's pretty bad. But it still has alcohol in it, so that's good. Number 2, and this one is 4. It has 4 carbons, so it's number 1. So you could say carbons up to 5 are good, and then past 6, it's not going to be soluble. So 6 is sick. So what it comes down to is the polar bonds, but rather you want hydrogen bonding first. That's like your priority. You got to look for that bad boy. Okay? So hydrogen bonding, the one with the least amount of carbons, is good. Polar is pretty good too, but it's way better than just having carbons. Carbons right here with nothing in it, terrible. For this problem, I want you to find out the functional groups that are in here. You can't do like a cheap cop-out and just say, oh, the whole thing's an alkane. Well, yeah, it's an alkane, but it's not really a functional group. It's more like a family of carbons, right? So we're not going to do that. Instead, you got to recognize some things. The easiest one, the give-me's, are these. It's just a carbon double bond. And a carbon double bond is called an alkene. I really butchered that one. So it's actually called alkene. And the easy way to remember that is that one bond is a king and the other bond is a queen. So king and queen, alkene. Cool. And this one is actually a carbon with an oxygen and the carbon 2, 4, 6, and 8. Well, I don't like that one. This is called an ether, right? It's an ether. And the oxygen is just surrounded in a sea of C's because you can have so many oxygen or carbons and you have one oxygen. Just lost in a sea of C's, and that's kind of like a wave of water. So an oxygen that is lost in a sea, like an ocean, of C's of carbons is an ether. So this one is going to be an ether. That's an ether. This is an alkene. Alkene. And this is not an aldehyde. This is not a hydrogen. Okay. And it's not a carboxylic acid. It's just carbon, oxygen, carbon, right? And that's a ketone because, well, it just is. The oxygen is all alone, but at least it has a double bond, so it's a ketone. All right? Just look out for that. Easy way to remember a ketone is that they occur in the middle of molecules. Sometimes they happen in the endpoints of a molecule. Like you could just be having this, and all of a sudden, oxygen, double bonded. You should know, hey, that's a ketone. All right. Same thing as before, I just want you to figure out the functional groups that are in this molecule. Well, this right here turns out that it's called a carboxylic acid. It's basically just a ketone connected to an alcohol group, right? So you have a carbon connected to another carbon that's double connected to an oxygen, and that carbon itself is connected to an alcohol, or if you like proper notation, an OH. So that's called a carboxylic acid. Carboxylic acid. Okay? Right. Now this one is a bit difficult, is it? It's a bit difficult because instinctively you would say, hey, this nitrogen group is a functional group. That's correct. And you would probably say, hey, it's an amide or an amide. Well, no, it's not. See, here's an amide. I call it amide. It would have a carbon, another carbon connected to an oxygen, And then you would have NH2. Now just notice, okay, that this nitrogen is directly connected to that carbon. It is directly connected to that carbon, and that carbon is directly connected to an oxygen, double bonded. However, amines are as follows. Carbon double bonded, right? Looks pretty similar. Then you have a carbon, and then you have NH2. Well, what's the difference? Well, notice that this nitrogen is connected to a carbon, but that carbon does not have an oxygen, okay? For a nitrogen to be classified as an amide or an amide, it would have to be connected to a carbon that has an oxygen to it. This carbon does not have an oxygen. It just has hydrogens. One way to remember this is that nitrogens, amides, have a seed. Amide have a seed. That oxygen kind of looks like a seed. So amides have a seed. And amines, well, they're all alone. They just have a carbon. And so they're mean people, right? They're negative because they have a negative charge. So they're mean people, all alone with just carbon surrounding them. Not cool. Don't like that. So in this case, do we have oxygens? No. We're just surrounded by carbons. And so we're mean people. We're going to be a mean. Right? Meanie. And this one, of course, is an alcohol. One way that you can remember alcohols is because they're very exciting, very high charged. Oh, I see an alcohol, right? Oh, I see an alcohol. Very exciting. Woo! Cool. So this is an arrow pushing problem, and here's how you go about it. So we have our given reactants. They're going to react and they're going to connect so that they make this product. But we got to describe how we made that product. What happened? Okay? Well, proper arrow pushing, it shows you if any new bonds occurred, if any bonds were destroyed, if any molecules got more negative or positive. So the main thing you want to check for is your negativity. Notice that right here, oxygen is double bonded and is neutral. But this right here, oxygen, is single bonded and is negative. So how do we describe that? Okay, well, to describe this, I want to have an electron connect right here. Oxygen is more electronegative, so it has a magnet that will connect the electrons. It will draw in the electrons. All right, so that gives us a molecule right here. So let's draw it out. Of course, you don't have to draw it out on the test, but it's just nicer to see, right? So we now have 2, 4, 6, 8. I would have 2, 4, 6, 8. So that'd be neutral. So you just have 2 more electrons. So 6 minus 6 is negative, or 6 minus 6 is 0, minus 1 bond is negative. So that is now negative. But then that carbon becomes kind of positive, right? Becomes positive. Because we don't have any electrons, we just kind of move the bond. So that carbon still has room in its valence shell to have electrons. And we got to find electrons somewhere. So how are we going to get electrons? Notice that this CH3 molecule kind of joined into that carbon. So it filled in that gap. How do we show that? Well, it's always nice to draw your electrons for these type of problems. So if carbon is negative, here's CH3, right? Here's CH3. How do we make this negative? Usually carbon has 4 electrons in it, so let's say 2, 4, 6, that's 8. So carbon has 4 electrons. 4 minus 2 electrons right here is 2, and 2 minus 3 is negative, right? So that's a negative charge. That means we have an electron or lone pair right here. Okay. So do we connect it like this? No, we don't. Because, again, carbon, right here, this carbon, doesn't have any electrons to give. So how can I give electrons to make a bond? That's not right. We make bridges, we make bonds out of electrons. And since this carbon right here has electrons, it's going to give its electrons to the positive carbon to make a bridge. So from here to there, we're going to connect. And what do we have? We end up having this nice, very nice structure like this, like that, CH3. So it connects, right? Cool. This is the same problem, or the same concept. We have two reactants, and they're going to react to make this product right here. How do we describe that with arrows? How do we push arrows, right? So whenever you're doing these types of problems, you always want to have your electrons drawn in. In this case, we have two hydrogens connected, so we have an oxygen connected to hydrogen, so that's kind of like water, right? And in this case, you would have two lone pairs on oxygen. Let's draw out your lone pairs. And nitrogen does not have any lone pairs, right? It does not have any lone pairs. It's like carbon, nitrogen, hydrogen, 2, 4, 6. Oh, it's double bonded, sorry. So 2, 4, 6, 8, it's neutral, it's actually positive. So 5 minus 1, 2, 3, 4, 4 bonds is positive. Doesn't have any lone pairs. What about this one? What about carbon, like nitrogen, and H? Well, 2, 4, 6, 7, 8. 5 minus 2 electrons is 3, and 3 minus 3 is neutral. So hey, this does have some lone pairs. This has some lone pairs. And notice that our oxygen actually transferred to this central carbon right here. So how do we describe that with arrow pushing? Well, the first thing I want to do is take care of that nitrogen. I want to take these two electrons and shift them to that nitrogen, giving us, this will give us this right here. And we became a little bit negative, so we're just going to have our electrons right there. Okay. But then again, since we took some carbons out of, we took some electrons out of carbon, this one becomes partial positive. How do we take care of that? Well, to take care of that, I'm going to go from my electrons to carbon. Carbon does not have any electrons to give, therefore this would be incorrect. Carbon cannot donate any electrons because it doesn't have any electrons to begin with. You can't donate money if you don't have any money, right? Oxygen has plenty of money, so it's just going to donate to carbon. And of course, this would give us the molecule that we'd want. So it would have kind of like this oxygen right there with the O2 or H2 and the nitrogen right there. And if you want like a blow up image of the oxygen, it looks like this. Okay, so 2, 4, 6, 7, 8. 6 minus 2 is 4, and 4 minus 3 becomes a partial positive. And that therefore describes us. Right. So again, always make sure that you're describing how you're losing bonds, how you're making something more negative or positive, and how you're making bonds. All right. What else? And yeah, that's pretty much it. Always make sure to draw in your electrons for any molecule. Like this one, we had to draw in our electrons right there. That helps a lot when you're transferring electrons to make bridges. Carbons that are positive, or things that are positive, like Na+, cannot make bridges. That's not right. Don't do that. Because we don't have any electrons to make bridges out of. But if something's negative, then you could connect it because it's going to donate Hopefully this helps. I hope you do well on your exam. We're going to do more practice problems later. Thank you.